What's good, everybody? My name is Professor Jennifer Hill and I run Divide and Conquer Math, which is a website dedicated to helping you learn math on your terms. This video is called a Study with a Math Professor video, and this is specifically on basic limits. So this is the first in my 4-part series on limits, and I have a lot of other videos dedicated to other topics in calculus and honestly other classes that I teach as well. So the inspiration for this video comes from my students who told me that they wish that we had more time to review things in class. And the problem with that is, one, usually the schedule for teaching is pretty stacked. I don't usually have that much time to actually go through review because I have so much I have to go through in a classroom. So I made these to kind of help my students, figure out, or go through extra problems. And I've covered a large range of material so that everybody can kind of get what they want out of these videos. The other thing about these videos, and the reason that there are 4 in this series, is that this really aligns with my personal belief on how studying should work. And if you're interested in hearing how I believe you should study for a test, I highly recommend that you check out this video right here, or you can look in the description below and you can find the link to that. So the way that these videos work is I'm not teaching you anymore how to study for a test. When it comes to studying for a test, you have to practice, practice, practice. Nothing is going to help you get prepared for a test more than doing that. So I have created these problem sets that you can access and kind of make what you need. So to get the problem set, check out the description below and you'll find a link to it and you can download it for free. You'll find a pretty long list of problems along with an answer key. Now, if you get the problems right, there's really no reason to have to go through and watch the solution in the video. But if you get the answer wrong and you want to see what the solution is, I've got you. And you can look in the description of this video for time markers for each problem on that sheet. Additionally, if you realize when you're doing a problem that you don't know how to do it, or you forgot how something works and you want to hear another explanation, you'll notice that on that sheet that I have recommended videos for you to watch in case you want more problems or more explanations. So basically, you've got everything that you need on that document and in this video. But like I said, the one thing I'm not doing here is I'm not teaching and I'm not necessarily reviewing. Now, if you are looking for just a summary of how all of limits fit together, I also have a summary video that might be really helpful to watch before you start this series, and of course you can also find that in the description. Okay, so the way that this is going to work is that for the first hour you will see me working on my own stuff, and I'm going to set a timer for about an hour. So if you're someone that has a lot of trouble getting started with studying, consider that to be a way to get yourself started, and you can work alongside me for an hour and I'll tell you when about an hour is up. Now, if you want to work for longer, feel free to hit pause, or you can start the video over. Make this whatever you need. If you don't want to watch the study session at all, then you can just look in the description and you can just flip through whatever problems that you want. So go download that problem set and let's get started. Hey guys, so I'm going to start doing the problems. So if you're not done, hit pause here. So this is probably one of the more basic type of limit problems. And in this case, you have really two continuous functions. So you can really just plug the 3 right in to this like so, since it's all continuous. And this just becomes 6 times 2. So this just equals 12. So if you didn't get this one, what I would recommend is looking up problems on your basic limit laws. So usually most calc books will have a section on basic limit laws, and I would recommend just trying to get through some of the other problems in that set. Practice a couple, maybe like 3 to 5, and then, when you're starting to get all of them correct in the back of the book, then move on. Okay, so for this problem, this is a rational function. And so, a lot of times you can really try these by just seeing if you can plug in the number and if anything happens, which in this case is totally fine. So I can just plug in -1 like this. And so what I end up getting is -3/2. And so that's the answer. So if you didn't get this one, once again, I would recommend that you check out problems on just the limit laws. So most calc books will have kind of the introductory section. Just make yourself do, like 3 to 5 extra. Do the odd problems, or usually the odd problems are in the back of the book. So just do a handful until you start to get them consistently right. So force yourself to do a bunch until you are getting it perfect. Okay, so for this problem, so this is really, once again, kind of just flexing on our limit laws. So notice this function here is continuous, so I can probably just plug this all in. So this is going to be 3 plus 5 to the 2/3. Okay, so if I evaluate this, this is going to be 8 to the 2/3, and then this will end up being, so first I take the cube root of 8. So the cube root of 8 is 2, and then I square it to get 4. So this is one of those problems where the tricky part might actually be the algebra for you. So if you find that that part is tricky, I do have videos on a review of exponents, which is like this is something you absolutely have to know for a calc class. So if you realize, oh yeah, I forgot how that works, don't just be like, oh, I forgot how that works and I'm not going to do anything about it. Force yourself to go back and just review some of this material. And another thing I would recommend that you try would be to find problems that look like this in the section on your basic limit laws. So where limits are usually first introduced, you'll probably see a handful of problems like this, and I would try some more just to make sure that you've got it. Okay, so moving on to D here. So now notice that we have the limit as x goes to infinity. So in our brain, we need to now shift to all of the techniques of what to do when x goes to infinity. And so this is really a rational expression that I can't really simplify any farther. So there's a trick specifically for when x is going to infinity where I can divide by the highest power of x. So in this case, I'm going to divide the top and bottom both by x to the 3rd. So if I do that, let me just show you what that looks like. Okay, and so here's kind of the setup. So I divide every single part by x cubed, and then I simplify this to 5 plus 3 over x minus 1 over x squared plus 7 over x cubed, and then all of that over 3 plus 2 over x squared minus 8 over x cubed. And the trick here is that really for all of these parts of the problem, this as x goes to infinity, all of this is going to go to 0. So the only thing that's not going to end up going to 0 are these two constants. So you're really just left with 5 over 3. And so that would be your answer. So if you didn't get this one, what I would recommend is taking a look at the section in your material or your whatever book you're using. So take a look at the section as limits go to infinity and just try some of like the first few problems. So try to do like 3 to 5 of them. Again, usually the odds will be in the back of the book, so you can double check your work, but make sure that you feel really confident with this and all the different ways this can kind of pop up, because this is kind of the basics of working with limits as x goes to infinity. And in other videos, we're going to be looking at more difficult examples. So you want to make sure you've got the basics down. Okay, so for E here, a lot of times people get really thrown off with the trig. And it's like you learn a whole bunch of things to do with trig limits. So then you start to think, oh, I have to apply this trig rule or that trig rule. And the thing about this is just your basic trig limit. There's nothing wrong with trying to see if you can just plug in 0 and making sure that nothing, if nothing bad happens, then you can really just kind of move on. So sine of 0 is just 0, so this just becomes 0 plus 1. So this whole thing just equals 1. I see a lot of times people really freak out when they see the trig limits because they know that there's like other things that you can do. So you just want to kind of recognize that a lot of times they can just be as simple as plugging something in. So if you didn't get this one right, what I would recommend that you do would be to go to either your section in your book on limit laws, or some books break out trig limits specifically, but just try to do some more basic trig limits. And so in the book that I use right now, there are just some trig problems in this section. So you can just flip and try a couple of those and practice and make sure that you've got it down. So for F here, so I said this in the last problem, but I'll say it again. So there's no harm in just trying to see what happens if you plug in 0. So if I plug in 0, this is what ends up happening. And I do not get 0 over 0 in this. So what I end up getting is I just get 2 over 5. And that's like a perfectly good answer. So, like this function is still continuous at 0 and nothing weird happens. So you can really just plug in 0. So I said this in the last problem, but I'll say it one more time. Sometimes people get really scared when they see trig, and the best way to deal with that then is to force yourself to do a bunch of trig problems. So I highly recommend, if you got this one wrong, force yourself to go into your book, and usually in the section that introduces limit laws, there's very often trig limits. That's how the book that I use works. But otherwise, just try to look where trig limits are introduced at first in your calculus book, and force yourself to do a bunch of problems on that just so that you can kind of get used to evaluating it. Trig does not go away in calculus, and so sometimes students think, oh, if I just ignore the trig, it will go away. That is not going to work. So you've really actually, if it's something that you struggle with, it's something that you're going to have to develop a mentality of, okay, I have to get better at this. So do not avoid the trig. Do not let yourself have that pass when you work through this. Okay, so for this limit, so what you'll notice is that you get 0 over 0. So 0 over 0 does not equal 1, but this is a theorem. So this actually is its own theorem. So I just wanted to bring up this basic fact. The theorem actually says that this does indeed equal 1. This equals 1. But it doesn't equal 1 because 0 over 0 equals 1. That is not a property. So this is something that you just have to know right now. It is kind of like just the basic fact. If you want to see why this equals 1, I have a whole video where I prove it. But for our purposes, I'm just going to say it's 1. And, if you forgot that, just remember it. We'll get to use this fact in other videos. So I don't even have necessarily anything for you to review. Okay, so for this one, so this is a limit that is approaching on the right. So the thing to kind of recognize with this is, why is it important that this approaches on the right? Well, because on the left side, this limit would not exist. But as far as our purposes for evaluating goes, it's really just as simple as getting to plug in the 1 in this case and getting to evaluate. So this is going to be 0 over 6. So the square root of 0 over 6 is just going to give me the square root of 0, which equals 0. So a lot of times when you're working with one-sided limits, it can be a very straightforward calculation like this. So if you didn't get this one right, what I would recommend, go to the section in your book that discusses one-sided limits, and then just try to force yourself to do a handful of some of the beginning problems. So again, 3 to 5 is usually like a good target. And just try to make sure that you get a bunch of them right in a row. So do a couple of the odds, double check in the back of the book that you got it right, and then move on after you've got it. Okay, so now we're going to move on to talking about the average rate of change. So I think these are pretty basic problems, although I think a lot of people forget actually how this works. So this is something that's covered at least in my book for limits and continuity, which is why I put it here. So for the average rate of change, really what you have to do is you take f of the two endpoints of your interval over the over the x values of that interval. So basically this is like the slope formula basically. So you just have to plug in these values. So what I'm going to get is let's see, f of 2 is 2 squared plus 1, and then let's see, this is going to be negative 2 squared plus 1, and then all of this over 4. So let's see, this will end up being 5 minus 5 over 4. So that's 0 over 4. So the average rate of change here would be 0. Okay, so now taking a look at this other problem, so finding the average rate of change here. So once again, so the formula for this is you're going to take the two endpoints and you're going to plug them into your function as shown, and then you just take the difference, really the distance between those two endpoints, like this. So now I can just plug everything in. So I've got sine of pi over 2 minus sine of 0 over pi over 2. So sine of pi over 2 is 1 and sine of 0 is 0. So this becomes 1 over pi over 2. And so then 1 divided by pi over 2 is equal to 1 times 2 over pi. So this ultimately just equals 2 over pi. So if you didn't get this one, I recommend that you look up problems on average rate of change. So I don't know that all calculus books will start off by talking about average rate of change, but the one that I use does. And so that's like one of our most beginning sections. So you can just kind of reference some problems there and refresh your memory. And again, do like 3 to 5 and make sure that you're getting them all right before you move on. Okay, so this is another set of problems that my book does. Not all calc books might do this, so you can of course omit this if your class does a different order. So we're going to use the difference quotient to find the slope of the curve at the given point and then the tangent line at that point. So starting with a here, so let me give myself some more space. Okay, so what I want to do is I really want to calculate the difference quotient. So here's the difference quotient, and so to do this at a point, I will ultimately assume that h equals 0, but the first thing that I need to do is really work all of this out. So if I work all of this out, I get 3 minus x plus h squared minus 3 minus x squared over h. And so now this is f of x plus h. That would be this first part minus the f of x. So I've got to just work all of this stuff out now. So this is going to be, let's see, 3 minus x squared plus 2xh plus h squared minus 3 plus x squared, all of this over h. Let me make some room. And so now I'm going to just be a completionist here, and I'm going to distribute that minus sign. Highly recommend that you show this level of work if you are somebody that is prone to making simple errors. This is a good way to slow your brain down. Okay, so let's see, the 3's drop out, the x squareds drop out, and so I'm left with negative 2xh minus h squared over h. So I can factor an h out of the top. Let's see, this becomes negative 2x minus h if I factor out one of these h's. And so now by factoring out that h, I can safely cancel this out. And so ultimately I get negative 2x minus h. Okay, so what the heck do you do with this? So let me now just get rid of all of this, and we'll just keep this negative 2x minus h. So we calculated the difference quotient and got negative 2x minus h. But to find a line that's actually tangent, or to find the tangent line at this point, so what that assumes is it assumes that h equals 0. So my slope then is given by negative 2x. So now I need to figure out what is the slope of the tangent line at this point, or the slope of the curve at this point. So at the point 1, 2, I'm going to plug in just the x part of the coordinate in here to get negative 2. So this is the slope of the curve at that point, 1, 2. So now notice what I've got here. I've got a slope. Maybe I should say this is really my slope. I've got a slope and I've got a point. Having a slope and a point is what will determine your tangent line. So to find your tangent line, to find my tangent line, I'm just going to use the point slope formula where I plug in my point and my slope. And so now I can just solve this. So let's see, I'll work on this over here. I'm running out of room. Y minus 2 equals negative 2 plus 2. And then I can go ahead and add the 2 to each side to get y equals negative 2x plus 4. And so there's my tangent line. So I've got the slope of the curve, and then the slope at that point on the curve, and then also the tangent line. Okay, so oops, here's the directions. So for this one, so use the difference quotient to find the slope of the curve at the given point and the tangent line at that point. So I've got this curve and this point. So I'm going to give myself a little extra space here. Okay, so the idea behind these is that you want to evaluate the difference quotient for this function. So there's the difference quotient. So I just really plug everything in. So I've got 1 over x plus h minus 1 over x, and then all of this over h. Okay, so I need to solve this as best I can. Now, what I like to do in my videos is I prefer to multiply by the LCD of all fractions, like you see here. And so what that's going to allow me to do is, see, I think I've got just enough space for it. So I've got x times x plus h times the first fraction minus x times x plus h, and then I've got the second fraction, and then all of this over h. And okay, so now what I'm going to do here is I'm going to cancel out so the denominators with this LCD. Oops, and I forgot to, sorry, my bad. All of this times x plus h, my bad. Okay, sorry. So back to the top. So here I cancel out the x plus h's, and then here I'm going to cancel out the x's. So now let me make some space. So now I'm going to have x minus h over h times x plus h. And that will simplify then to just negative h over hx times x plus h. So then my h's will cancel out, and I'm left with negative 1 over x times x plus h. And so remember, we said that we are assuming that h equals 0. So for this to be a tangent line, you have to assume that h is 0. So this will actually become then 1 over x times x, oops, sorry, negative 1 over x times x, which is negative 1 over x squared. Okay, so what is this? Let me make some space. So this result right here is literally telling you how to find the slope at a given point for this particular curve. So at the point 2, 1/2, my slope at the curve at this point will be found by just plugging in the x coordinate like this. So the slope in this case would be negative 1/4. And then from here, we can find the tangent line. So to find a tangent line, to find the equation of any line, you need a slope right here, and you need a point, which we also have. So using that information, I can use the point slope form of a line. Oops, let me grab the white color. So this will be y minus 1/2 equals negative 1/4 times x minus 2. And so let's see, I can simplify this. So this becomes y minus 1/2 equals negative 1/4 x plus 1/2. And then I can add, let's see, the 1/2 to each side, like that. So I get y equals negative 1/4 x plus 1. And so there is the tangent line in this case. So if you missed this one, you can just go and find other problems that look like this. And again, practice like 3 to 5. And when you are getting them consistently right, then you can move on. So now we want to determine the intervals of continuity. And so it can be helpful to to know a little bit about each type of function when you're looking at this. So this is a line. So a line is just always continuous. So in this case, your interval of continuity would just go from negative infinity to positive infinity, and that's really it. So if you missed that one, you might want to go back and review just what the basic idea of continuity is. And then also I would go to the section that talks about continuity and just do some of the beginning problems. And there's almost always some problems on finding like intervals of continuity. So that's what I would do if you missed this one. Okay, so for this one, once again, we want to determine the intervals of continuity. So the big thing to notice here is that this is a rational exponent and this is squared. So another way that I could think about this is I could think about this as the square root of x cubed. So this really matters because you have to know something about like your even and odd roots. So if you forgot that, that might be a thing you want to look up, is the domain of even and odd roots. This is like an algebra thing that you have to know for calculus because this will come up a lot. So really, the only, when it comes to the domain of a square root or an even root, it has to be, this thing under the radical has to be greater than or equal to 0. So if that's what my domain has to be, then that's actually going to be my interval of continuity in this case. So my domain, or my interval for continuity, starts at 0 and goes to infinity. So it literally just ends at 0 because we have nothing really beyond that. We can't plug in anything, so it can't be continuous after, when you go past 0, if that makes sense. Okay, so for this problem, so thinking about just intervals of continuity, so now we have an odd root, and so just as a reminder, if you didn't know what to do with this one because you weren't sure about the exponent, I would recommend going back and reading about even and odd roots. Like that's something that you could just Google and kind of refresh your memory on. Or you can look in my review videos where I talk about rational exponents. So either option works. So in this case, this is a fifth root. That's ultimately what I care about. I don't really care about what's going on the top. It just really matters what's happening in the bottom. Since this is an odd root, I can take the odd root of any number. So this is really just going to always be continuous. So I don't have to worry about any continuity issues. Okay, so for D, so trying to determine the intervals of continuity for this one, so you definitely need to know the graph of tangent. So if that is something that is a sticking point for you, that's really, really common. And it's like super important when you are in Calc 1. You're going to use lots of trig when you get to Calc 2. So you can't let yourself have a pass on this being a weakness. So if you forgot the graph of tangent, like actually just sit down and force yourself to like regraph it and try to remember. So the thing with tangent is that tangent actually does have values that won't work. So basically anytime you have, let's say like an odd root of pi over 2, that's going to be a problem. So basically what I'm interested in is when will this x over 2 give me an odd, like an odd multiple of pi over 2. So the way to represent that, any general odd number would look like this, 2n minus 1. Put in any number that you want for n, and this result will give you an odd number. So if I put in 2, this will become 4 minus 1, that'll be 3. If I put in 3, this will be 6 minus 1, which will be 5. So this is how you represent just in general odd numbers. And I can't have an odd integer of pi over 2. So basically, this is what I want x over 2 to not equal. So I just want to figure out what is the format of this. So if I solve for x, so multiplying both sides by 2, that cancels out. So anytime x is equal to some odd number times pi, we're going to have a problem. So I did this work to help me figure out what I need. So this is kind of like my scratch work. And then what I would say for my answer is that this is continuous everywhere except when x equals 2 pi minus 1, or sorry, 2n, not, why am I, it's been a long day. Okay, 2n minus 1 times pi. Okay, so there's not like a great interval notation way to represent this. You kind of just have to write it out in this case. So if you forgot this, I highly recommend that you just review your trig graphs and domains. This is something that you'll probably have to continuously go back to review. I'll be honest, I mean, sometimes I, like, depending on how long it's been, I still have to go back and review like certain trig graphs. So it's really common to have to go back and do that. So if this is something that you're using right now, you're going to want to go back and review that. Okay, so moving on to these questions. So this is just like a little picture that I drew. And so we're going to find the limit based on the picture. So first, starting with the limit as x approaches negative infinity. So here's the negative infinity direction going this way. So I can see that this is actually getting really close to this asymptote right here, which is just -6. So this equals -6. So if you missed that, I would recommend going back and looking at just like your limits at infinity type problems. And usually there's like a couple of graphs you can do like in any book, so you can just kind of refresh some of those problems on your own. Okay, so moving on here to really like the next 4 problems kind of have to all relate with one another. Okay, so this is talking about the limit as x approaches -5 on the right. So here is -5 right here. So this plus sign means that I want to be on the more positive side of this. So just to be nice and explicit here, so here's 5, right? Here's where 5 is. So which side is more positive, this side or this side? It would be on this side. So this is the part of the graph that I want to be on to evaluate my limit. So I'm on this part of the graph, and then I'm just going along up to -5, and then it looks like here for that this would be going to negative, or that this would be going to 2. This would be going to 2. Okay, but now if I pivot and say what about -5 on the left, well, that would be on this side. This is the more negative side. And I have a whole video where I break all this down, so if you need a refresher of that, you can look up my video on one-sided limits. So I would be on this graph here, and as I'm following along, now it looks like the limit would be going to -4. So this would equal -4. So what about then the limit is just x approaches -5? Well, you can see here that it's approaching 2 different values. So this would be a case where the limit does not exist. So now there's the question of what kind of continuity exists at x equals -5. So this is always a tough one. So your continuity has to exist when f of that limit is equal to the limit. So basically what I'm trying to get at, so this we said was equal to 2. We said this was equal to -4. And so really the other piece of information that you need to know, what is f of -5? What does that actually equal? Well, f of -5, if I look at the graph, f of -5 equals 2 because that's where the filled in dot is, right? So this would equal 2. So when these two values are the same, that's your type of continuity. So the limit itself does not exist, but on the right, that's what equals the functional value. So what type of continuity exists then at x equals -5? It would be right continuity. If that doesn't make sense, or if you need a refresher on that, I do have a video explaining and breaking down continuity that you can go back and watch. So check out my video on continuity if you need more help. Okay, so moving on to f and g here. So again, kind of related. So looking at the limit as x approaches -2, this is like a problem that always kind of surprises me. So students get this at first, and then sometimes they'll start to make mistakes on this. So notice, on the left and on the right, I know there's a hole here, but that's the whole point of a limit. It looks like it's approaching a particular value, right? The value it looks like it's approaching is 2. So that would be the value of this limit. But then when I ask what type of continuity exists at f of -2, well, here's the question that you have to ask yourself. What is the value of f of -2? If I look at the value of f of -2, it's actually up here, right? It's 5. So this equals 5. These two values are not the same, so there is no continuity. There's none. There's nothing. It's actually discontinuous at this point. So that's kind of the idea behind that. Again, if you need a refresher on this, I do have a whole video on continuity. I highly recommend you check it out. Okay, so moving on to h and I now. So now I want to see the limit as x approaches 6 from the right. So, okay, so at 6, here's where 6 is. It's right here at this asymptote, okay? So on the right side, again, if I look at this and I think where's the more positive side, that would be this side. So on the right, this is going to down, 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 so that's -infinity. Versus on the left, so now this is the more negative side, and this is going up. So that's positive infinity. And then finally, what happens is to the limit as x approaches just infinity? Well, I can see here that I've got this asymptote. This is an asymptote at 3, so that's what it looks like it's approaching. So this will be going to 3. Okay. Okay guys, so that covers it for this video. If you're interested in checking out more, check out the description. I've got links to plenty more videos where that came from. Thanks for watching guys. I'll catch you next time.